Hey, so I'm Alex, and I'm going to talk to you about a project we undertook to autoscale our stack using custom Prometheus metrics and AWS. Who am I? What is a style? So my name is Alex, and this year I'm leading the product engineering team at Style Education. Last year I led our SRE and infrastructure team, which is why I'm giving the presentation on this issue. We're a very small company, about 45 people in total. Our infrastructure team at the time was 2 core members and others contributing part-time. So very small team. And our mission is that we're trying to improve teaching and learning in secondary school science. So on the technical side, it's a web platform where students and teachers collaborate using interactive worksheets. So if you visualize something similar to Google Docs, where users input stuff and save data constantly to an API, that's basically all you need to know from an engineering standpoint about the problem we're trying to solve. So I'm going to describe to you a real project that we completed that saved us a lot of money. The big challenge for us was to move from an entirely static deployment to one that scaled with demand. Entirely static is maybe a little unfair. We deploy daily through a red-black deploy process. So we spin up an entirely new set of servers running new code, and then we cut over at the load balancer to the new stack from the old stack. But for the duration of that day, for the duration of that stack's lifestyle, the servers were static, they just sat there. So if you similarly are looking for a way to auto-scale a static stack to save money, I'm hoping that this will, for one, help validate for you that this is totally achievable and suggest some traps to watch out for and encourage you to give it a go. If you already have a super robust auto-scaling system, then perhaps you can just commiserate with us and enjoy the talk. I'm a little bit curious, actually, to where the people in this audience see themselves. Perhaps if you want to, post in the chat static or dynamic, for if you think of your stack as mostly static or mostly dynamic. So motivation for us, because we're an education product, we have a daily traffic cycle. We are mostly used inside classrooms. So during the day, we have this massive peak at from about 8:45 to about 9:15, during which all of our users come online, which is really hard for our stack to handle. So we're constantly over-provisioned. So the actual request rate coming in that this, what we call the back-end stack, is handling is, you can imagine, over a given week, it's actually fully utilized much less than half of the time. We also have what we call our async stack. So whereas the backend stack handles requests that the client needs an answer to right now, any work done that could be done a little later, for example, invalidating caches or otherwise responding to something in the background, will happen on a separate set of servers that we refer to as our async stack via a message queue. So similarly, this also shows a strong daily cycle, but unlike the backend stack, it's actually even spikier. I've filtered it in the top graph for a messages published rate less than 10,000 to show you what the normal traffic looks like. But the unfiltered graph shows spikes up to 100 or 150,000. So it can be extremely spiky. And further to that, the actual CPU usage doesn't correlate well with the messages published. And that's because this stack is also doing a bunch of batch work overnight, handling cron jobs and audit tasks that don't actually correspond well to a message rate. So this stack needs a very different set of scaling parameters. And it's far harder to predict the demand in advance. So I think you should be starting to see here the motivation here for time-based scaling of some kind, and here for resource-based scaling of some kind. The business case is really easy to make. There's this huge gap between what we pay for and what we actually use, and that gap is wasted money. So if you're trying to convince anyone else in the business that this is worthwhile, just show them a graph like that. So we're in the cloud, we're using AWS autoscaling groups. Why don't we just make them autoscale? So the takeaway I want you to take from this is that actually autoscaling is the easy problem. The hard problem is moving from long-lived instances to short-lived instances. And the other hard problem is making sure that you're confident that this system is designed not to ever endanger the functionality of your app. So we did achieve this in the end. This is what success looks like. This is a view into the brain of our autopilot system as measured by certain metrics. The sort of square wave at the bottom is the time-based scaling metric. So it scales up just before that morning peak. And then the CPU-based metrics take over to handle the rest of the day. And there's no longer any significant gap except at nighttime where we just don't want to scale down to 0. So we keep 3 instances around at all times. So there's a long road between where we were and getting to here, which we're going to go through now. To start with, how do we know what to target? Targeting CPU utilization makes sense because it's the main resource provided by these servers. However, there is a trade-off between latency and cost savings. So the lower the target for CPU, if you aim to use no more than 20% CPU, you're going to have basically no time spent waiting to get access to a CPU when a request comes in, and your latency is going to be fantastic. Conversely, that will also cost you 4 times as much as targeting an 80% CPU utilization. So somewhere in between, you want to find a good balance where your latency is acceptable and your costs are acceptable. You also want to be worried about your ability to absorb sudden spikes in traffic, and you want to make sure that there are limits on minimums and maximums that are tested and safe. So in this graph I've got here, the 3 curly lines on the bottom, sorry, this one's a bit confusing, are our latency percentiles, 50th, 85, and 99. And the top line is actually using the right-hand axis, and that's the CPU utilization. So you do see a strong correlation between high CPU and high response times. Of course, it's not as simple as that. There's a huge impact from database load and tuning of other parameters. But that is one aspect of the trade-off you'll need to choose. Similarly for the async stack, there are parameters you want to tune around. They're not latency related anymore, but we do want to set some sort of standard around how much time it's acceptable for messages to queue before they get processed. We want to have a think about whether there are message priorities, that some messages need to be processed quickly and some can take longer. And we want to tune other parameters to make sure that they're actually getting through those messages at an acceptable rate. What I'm getting at with both of these slides is that you need an SLO. If you don't already have an SLO that spells out what the demands on your application are and what acceptable delays are, tackle that first, because until you know what the acceptable goalposts are, you won't know where you're aiming for. Some constraints on the project. We had at the time a fairly complicated app with real users. We had at peak times of day about 10,000 users logged in using the app, which meant we definitely didn't want to cause too much disruption. We're actually now up at around 50,000 since COVID, which has been a story in and of itself. But anyway, there are things to lose if we stuff this up. We want to make sure that the solution is easy to operate so that the on-call team can get behind it and be confident that they can shut it down if they need to and that they can understand how it works. And probably most critically, we don't actually want to sink too much time into a project like this because the opportunity costs for a small company with a very small team are huge. So if the project takes too long to implement, we will lose in engineering hours and productivity and opportunity what we gained back in cost savings. So fundamentally, we want a simple solution that's not too hard to implement and is easy to operate and is not going to endanger reliability. In other words, we weren't going to rewrite to Lambda or any other serverless solution. We needed to sort of stick with what we had and build on that. So some of the AWS savvy amongst you may be thinking, well, AWS autoscaling provides CPU and time-based scaling. Why not just turn it on? So we very, very seriously considered that, and we sort of tried to do it a few times and got cold feet each time. We were just really worried about unknown impacts from moving to long-lived to short-lived instances. And fundamentally, we didn't trust CloudWatch events to be reliable enough for our purposes, and we were worried that we might not be able to scale up when we needed to. So in other words, we didn't trust that enabling that parameter would actually preserve our reliability standards. And also, point number 3, the easy part is actually changing the desired capacity of a scaling group. The hard part is making sure that that doesn't destroy your application. So the AWS solution would have only solved the easy parts for us anyway. To illustrate what I mean by that, some issues we had, we simply didn't have good drain and termination handling code in our APIs because we hadn't needed it. All of the load was getting moved onto the new stack before the old stack terminated during our daily deploys. So instances actually being terminated under load was very rare. But if it was going to be happening hundreds of times a day, we needed to make sure that that was actually not causing errors. Our load balancer is HA proxy. At the time we were using version 1. And its idea of live config is that it's possible to write a clever script to restart it without dropping requests, but the server does turn off and on again. So we were a bit concerned about doing that as well. And also it would just any long-lived connections, for example, sending server-sent events. We were particularly worried because we're only hosted in AWS Sydney, that if the scaling group is using a particular instance type and AWS runs out of capacity in that region for that instance type, that we just wouldn't be able to scale up. Once that happens, you're probably going to experience cascading failure modes where the remaining instances are taking on too much traffic and choking out. So you sort of want to not be in that situation. We were also worried that we hadn't tested instances starting up under pressure. Previously, we'd relied on having some time to health check them using a script rather than an ongoing health check before we directed the load balancer to give them traffic. So obviously we wouldn't be able to do that anymore. And we were finally also worried that the AWS CPU and time-based scaling might just not be flexible enough or configurable enough to actually meet our needs. And we would end up re-implementing something anyway. So if we're going to move to short-lived instances, we started tackling these problems. One thing we realized is that servers would have to start quickly. So we're running EC2 instances in a scaling group that run Docker Compose and pull containers in order to start. Foolishly, we'd had that configured just to run in serial. Simply choosing to pull those containers in parallel took us from about a 12-minute time to about a 2-minute start time, which was a huge win. We solved the problem of concerns about capacity because fortuitously, at about the time we were this project, AWS released their mixed instances policy, which allowed you to configure a list of fallback instance types that you're willing to accept, even if they're not ideal, which made us a lot more confident about about being able to scale up. We also considered 2 further solutions, just getting our Docker containers to be a lot less bloated so that we could quickly pull the bytes over the network. And we also considered using Packer to create a custom AMI for every stack. This would have been the fastest solution, but honestly, we didn't end up needing it. 2 to 3 minutes was acceptable. So that wasn't too hard. Then we tackled the idea that servers would have to gracefully shut down under load. Thankfully, there's lots of material on the internet that you can research to know how to handle this properly. So we introduced what's called a lame duck period, where you tell your servers that they are shutting down, they begin deliberately failing their health checks and refusing to take on new work, but are still allowed a few seconds to finish off existing work. We tested and all of our actual termination handlers turned out not to work very well either because they hadn't been exercised very regularly, so we dug into that. We started tagging the logs centering instance shutdown so that we could make sure that we were noticing if we were getting undue errors in that period. And despite all that, nothing seemed to be working. We were not getting logs shipped from instances that were shutting down. They were spewing errors. And we couldn't quite figure out why. Eventually, we realized that you also need an instance level shutdown handler to control the order that your Docker containers are killed in, because our FileBeat container was getting killed by Docker before our main app container. It was surprisingly finicky to get all of this right. I would say this is probably the single hardest part, which we did not expect. To illustrate what an instance level shutdown handler looks like, here's a wall of code. I suppose I'll probably make this available to the meetup at some point. Not that you should copy it precisely, just to give you a general idea of how you might want to write a thing like this. So this runs on the instance beginning to shut down. It carefully disables the restart policies that would attempt to start Docker containers again. It disables a Docker container that has the job of restarting other containers and running health checks. Then it kills our main app, waits a few seconds, and then kills the log shipper. The final problem with short-lived instances that we also didn't anticipate was simply in handling churn. So we did previously have tasks that ran for hours, and we hadn't even necessarily noticed that they were running for so long because they were still succeeding. So we ended up writing running a whole project to create a thing we now call Migration Manager, which is designed to break up long-running jobs into tiny pieces, which ended up being necessary for this as well. Then the remaining problem we had with churn was that long-lived connections were being terminated by HA proxy. The problem with that, even though our app does handle reconnections fairly gracefully, is that you would get 30 seconds to a minute after each restart where those events weren't coming through. So since it's a collaborative app that's used in classrooms, it's actually quite noticeable if it doesn't receive updates for as long as 30 seconds. So it's a poor user experience, and this might be happening, many times per hour. And it was also causing undue load on our API because as those connections were reestablished, additional queries were made to see if the service had missed out on anything by accident. So we got very spiky load, which became much more of a problem recently during COVID when we had to suddenly scale to 5 times our usual traffic. Any sort of deviation from a smooth traffic line was suddenly hugely expensive and damaging. So we actually ended up turning off our autopilot system for a few weeks while we fixed this. We did eventually fix it by updating to HA Proxy 2 and doing some enormous hacks to implement their live config via their stats socket. The way this works is that HA Proxy has a fixed size memory buffer for servers, so you can't load balance them live, but you can allocate 1,000 servers and then update their IP addresses live and have some of them be fake. That's what we did. This is an illustration of the before. So this is a graph of our SSE connections, server-sent events. So they're long-lived HTTP connections to each client. Those dips are when the restarts happen, aka an auto-scaling event happens. And I should explain, the reason that needs a restart is just because a server has been removed or added that the load balancer needs to know about, and restarting is how it gets that update. So this was a huge win. So the right hand and bottom middle graphs are showing the 2 stacks scaling down. They're scaling down, about once every couple of minutes, and there's just absolutely no impact on request rate or response time or the SSE connections. So that's worked really well. Okay, so that was hard problem number 1. we're now at a point where we can actually safely remove and add instances without causing damage. That was actually by far the hardest challenge we faced. Problem number 2 was getting to the point where we were confident that autopilot would behave correctly and safely. We do not want it to reduce our overall reliability at this stage in our company's life. It's more important that we're reliable than cost effective, but we also need money. So we do want to save money, but not at the cost of reliability. Failure to scale up is particularly concerning. We don't want to add a lot of complexity, and we don't want to create a whole elaborate control plane that the on-call team will need to learn to use instead of being able to use built-in EC2 console and other tools. So what we designed in the end is a system that can only set the desired capacity. So during an outage or for whatever reason, the on-call team can continue to use the EC2 console to set the size of the scaling group, and they can disable auto-scaling simply by making the minimum and maximum capacity of the group equal to the desired capacity. Autopilot does not have permission to change the minimum or maximum, and EC2 won't let you change the desired capacity to be outside those ranges. So this made a simple way to shut it down. There's other ways too, but that's the sort of fail-safe one. The other key conclusion we came to is that autopilot should handle any sort of failure by scaling all groups it knows about to their maximum size. So if it's missing data or any other errors occur, it will simply scale everything up to maximum. This costs us money, but saves us reliability. Finally, we wanted to make sure that autopilot was not actually broken by us updating it with incorrect code that we'd somehow missed out in testing. For example, we wouldn't want to accidentally change the permissions model such that it no longer had permission to alter the desired capacity. So whenever we deploy a new stack, autopilot does self-test itself in production to make sure that it can set the desired capacity. So between the few of these things, we've got enough confidence we can deploy it. In terms of simplicity, we wanted to avoid adding any stateful services. So autopilot is just a Docker container that runs on our async stack. It takes a lock from console to become the autopilot master. All of its state in terms of what it knows about the world is stored in Prometheus, an open source monitoring system that we use. So that includes all of the information about the systems that it's monitoring, for example, their CPU utilization or any other metric you might be interested in collecting, as well as its own metrics about how many instances it's created or removed recently, which we use to implement smoothing. So autopilot simply queries Prometheus to find out if it itself has changed the desired capacity recently, and if so, it doesn't change it again, just to implement some smoothing. It's also configured entirely through console, so it makes it easy for us to tune estimates of what the stack size should be at certain times of day without having to redeploy any code. Finally, we needed to come up with a convenient way for developers to introduce new metrics that they wanted to auto-scale based on. So we came up with this concept of targets. So basically what you do is you give autopilot a target number and you give it a Prometheus query, and autopilot will then take over the work of smoothly adjusting the stack sizes until the query result matches the target result. Another key component here is that the final capacity chosen is a maximum of all the targets. So if you want to introduce a new target, you never accidentally underscale the stack. The worst case scenario is that you incorrectly overscale the stack. That made it a really safe environment to experiment with. What does that look like in code? So we ended up with a fairly simple config, as I just described, where you have a, can you guys see my mouse cursor, by the way, if I move it around? I'm assuming, yeah, okay, cool. So you've got your CPU target, which I've broken out here. So we're targeting 60% utilization. We add a Prometheus query. This is important. We add an up expression as well. So autopilot needs to know how many instances are actually handling this sort of traffic. So that's what the up expression is. If you're not familiar with Prometheus, up is a special metric that indicates that the service is running. This lets us avoid configuring other common variables like what the expected start time of a server is, we can simply wait until we see the up number change, and then we know that the scaling has happened. Hyperbolic scaling is about understanding that CPU is a constrained resource. It can never be 1.8, it can only get to 1, which means that when we get close to 90 or above % utilization, Autopilot needs to really scale up hard because it's no longer able to really estimate what is needed. When we're doing our red-black deploys, we actually measure the production stack's CPU usage in addition to our own CPU usage, so that we can sort of start off on approximately the right scale. And we also have a bunch of constraint-based metrics, which are other reasons in our system that can be addressed by scaling that aren't CPU, such as thread pools, MySQL connection pools, and finally we have our hand-coded time of day prediction. That initial morning peak is so steep that it's critical that we have a time of day prediction to initially scale up before that peak hits. The nice thing is that it's now very easy to experiment with. This is the easy problem now. If we want to try machine learning or estimating the current size based on the peak load 7 days ago in a 20-minute window, we can simply add another predictor and another Prometheus query for that. In terms of other constraints we might find, it's always possible to add those constraint scalings as well. In my opinion, all of this is basically not needed. If you're scaling on anything other than time or CPU, you're probably in a situation where the system isn't tuned correctly rather than needing a scaling solution. But that's an ongoing subject of debate at our company. That said, mostly we have found that time CPU and hyperbolic CPU are good enough if the instance is well tuned. The key consideration when you're deciding what to scale on is whether scaling will actually address the constrained resource. So that's what's good about CPU-based scaling. No one can question that adding more instances is going to increase the number of CPU cores available. Same with memory. Other issues like an overutilized thread pool that's stopping it from reaching its peak CPU, you can solve that sort of thing through scaling, but it's not scaling that is the ideal solution. It's changing the tuning of that system so that CPU ends up being the real constraint. Overall, this was actually a huge success. It was way harder than we expected it would be, mainly due to that reason number one there. Moving from long-lived to short-lived instances was just extremely fiddly to get right, and there was probably, since we launched Autopilot, a long tail over maybe 6 or 8 months in which we kept finding bugs related to having moved from long-lived to short-lived instances. So if you take nothing else away, it's totally achievable, but expect a long tail of work associated with that transition. We were very happy with the system design in the end. It has delivered its promises of being fault tolerant and letting us have lots of flexibility in what we choose to scale based on. Yeah, and actually choosing what to scale on, we basically ended up back where we started and saying CPU and time are enough. So question, did you find you needed to do anything special to sync up HA proxy to app service discovery with instances coming going? So I think KJ has asked that question and he actually wrote most of that code. So we use console for service discovery, and we use console template to write out an HA proxy config. And then we use some clever code wrote to restart HA proxy to load the new config without dropping any queries by simultaneously listening on the socket with both the old and the new service. Is that what you meant, KJ, or something else?
As much as I love asking a question that announces how clever I am about all the code that I wrote, what I was actually asking was about whether you, as part of that magic shutdown script, had to do anything to like let HA proxy know that it was going away before.
Gotcha. So we just rely on HA proxy health checks. There's a flash ping route on our app that HA proxy queries we tuned that down from, I think, 5 seconds to half a second. So we simply started failing that ping route. At 3 failures, HA proxy would mark it as drained and stop sending traffic. So took about 1.5 seconds in total and just allowed us to avoid having to add a different, just allowed us to avoid adding a special sync up with HA proxy at that stage.
That makes sense.
Cool. Fail by scaling to max. This absolutely does cause risk of cascading failures, and we have experienced that for sure. One of the things on my gotcha slide that I sort of skipped over is that you must absolutely test your stack at the maximum sizes you configure, not just at the sizes you expect to experience on a day-to-day basis. We've experienced a bunch of different failure modes where scaling up to max while the system is under pressure has increased the pressure rather than decreasing it and caused the situation to worsen. This especially happens when a slowdown has been caused by the database rather than by the application stack. And that slowdown has in turn caused the Slack to appear to be busier or slower. And then scaling it up again increases connections to the database and slows down the database and can trigger a cascading failure. So you want to be very sure that under high load, at maximum scales, your system works fine. Otherwise, you're almost guaranteed to end up in a situation where scaling makes the situation worse. We also had a fun gotcha where we accidentally quadraticed in terms of our message handling. We had a broadcast route, which would cause every instance to do a small amount of work and the message bus itself to do a bunch of work. So as the app scaled, it would do more work and scale more. So that was fun as well. Docker on VRC2, absolutely. The only reason we're not using Kubernetes or another orchestration solution is that at the time we put together this configuration, it wasn't available or robust. So it's absolutely on the cards for us, probably something we'll be looking at next year to move to Kubernetes. Autopilot is just the name we've given our custom solution. Any thought of separating the batch processing out into another group or instance type for longer running processes? Absolutely. That's something I think we ought to tackle. In general, I think I like the architecture of breaking long running processes up into short ones because it does sort of work well with an auto-scaling model. It does allow you to sort of burst to meet demand. But in practice, having a batch stack would have also solved that problem really well. And Scott, what does the stack consist of? So there's 2 stacks I'm talking about. So we've got a backend stack handling quick responses, and then via a message queue going to another stack, which I call our async stack, which is handling slower stuff. Is that what you meant? Oh, refactoring the code to make it more efficient, as in, yes, okay, that's a really good point. So we've got a problem where we're using money to buy computers to run our code. A reasonable solution, which we did consider, is to try to make the code faster. Simply thought it would be more difficult and more expensive to go down that path. Our app's written in, it's a Ruby microservices architecture. We'd already done a bunch of improvements that we could think of to make that faster. The sort of next steps we were considering to make it faster were on the order of rewriting it into another programming language, which seemed extremely expensive to us.
Okay, all right.
Thanks so much, everyone.
Awesome. Thank you so much, Alex.